So let's go ahead and continue here the discussion 3.4. In 3.4, we're dealing with the ideal gas law. That reaction or that equation is equal to PV is equal to nRT. Now there's a lot of variables here that you need to be aware of, so let's just identify them here quickly here. The P stands for the pressure, but main thing here with the pressure is that you need to remember the standard units. The standard unit of pressure here with the ideal gas law is 1 atmosphere of pressure. The volume is the volume associated with gas at 1 atmosphere of pressure and at standard temperature, which is 273 degrees Kelvin. But the volume that's occupied at those temperature variables and pressure is 22.4 liters. The number N, or the letter N here, represents the number of moles, and the standard unit for the moles is 1 mol, 1 mole. The R is the ideal gas constant, so I'm going to show you that here in a second. I'll just put an asterisk above it. But the T here is the temperature, and the unit standard unit is 273 Kelvin. So just quickly review the way that you get the Kelvin here. Remember, you get the degrees Celsius, you add 273. That's how you get that. The number of moles here can be derived by the mass of the particle over the molar mass, and I'll abbreviate that with 2 big M's, is how we can get that. And then the atmosphere, there will be no conversions, at least on my quiz here, but remember that on the AP exam, you can definitely find some conversion problems that I will have you convert from, say, torr, from millimeters of mercury or pascals into atmospheres, but for my exam, I'm not going to have that, at least on this go-around here. The thing that you need to be able to do here is to identify the relationships between the variables. So identify how pressure is related to the volume, to the temperature, and all that. So the one way that we can do this is if we take the equation PV equals nRT, and let's just isolate the pressure variable here and bring the volume over to the right side. So let's just divide by V on both sides. That will give us here pressure is equal to nRT over V. And so here we can start to see the relationships that are occurring here. Pressure is essentially going to be inversely related. It's proportional to 1 over the volume here. Pressure is directly related to the temperature, and pressure is related to the number of moles here. Now, the various gas laws can be summarized in one major gas law. So let's go ahead and do this. Let's go ahead and kind of put these things together. Let's move some stuff over here to the right. And the gas laws, I'll just give you the main one here, the combined gas law. And so that would be the P1 V1 over T1, and that's going to be equal to P2 V2 over T2. And so here, when you consider the items here, the variables, anything that's kept constant can be essentially eliminated from the formula. For example, let's go ahead and put in Avogadro's number here, or the number of moles, so we can have Avogadro's at play. And so what if we kept, say, pressure and temperature constant? So essentially these variables would be erased from the mix, and so then we would wind up getting here V1 over N1 equal V2 over N2, which essentially is Avogadro's. So the main thing that you want to be able to do is just to remember which of these variables are going to be the variables that are going to be kept constant. So make sure you read the stem of the question and see if you can determine that. The other item that you'll need to make sure that you know is how to derive the pressure of a gas, either a collection of gas, so that means the total pressure. And so remember here that the total pressure is going to be just the sum of the individual pressures exerted by any gases in a mixture. So for example, if there were 3 gases in the mix here, we would have the pressure of the first gas plus the pressure of the second gas plus the pressure of the third. In this case, I'll just put that as a little n, because you can use that generically if there were 4 or 5 or more gases. That's how the way you would figure out the pressure total of a system, is identify the pressures of each individual one. However, if the problem is asking you to find the pressure of any individual gas, let's say that you're trying to figure out the individual pressure of the gas, then we can actually separate that out and say that the individual pressure of a gas, and let's say that's gas, say 1 here, because that's the number I used, the pressure of the first gas is going to be equal to the mole ratio of that gas multiplied by the total pressure. And in this case here, total pressure is probably going to be given to you because it will be presented as the pressure of the system. So how do you get this value here for x1? Well, all you really need to do there is to take the number of moles of the gas itself and divide that by the total moles. And that's how you get that value there. And then once you know that value, which is x1, multiply it by P total, and that'll give you the pressure of the first gas. So now that we're here, the main thing that we also need to talk to you about, let's kind of make some space here, move some of this stuff over here, is what about mixing of gases? What happens when we have these gases mix? Well, one key point that you should remember or just keep close to you, forefront of your memory here, is going to be that any gases, when they mix, these gases will readily mix. And they're going to try to mix evenly. So in whatever container you tend to have them in, they will eventually mix so that they're evenly distributed throughout the space that they're in. In a separate section, we're going to talk about what happens when you put them into a container, seal them, and then allow them to escape. There is a relationship there where we'll need to look at as well. But we'll talk about that in the next section here in 3.5. I believe that's in 3.5. So one other item that you would need to be concerned about is being able to calculate problems that involve density and molar mass. And so that's important. So let's kind of address that here in a second. Being able to address them essentially means that you're able to go from the ideal gas law, PV equals nRT, and that you're able to identify here that the variable n here can actually be represented as the mass divided by the molar mass. And so we kind of set that over here on the right hand side. You'll see that it's already there. So if we replace that there, this variable here, we can have mass over the molar mass, and this is going to be times RT. And then if we get this equation here where we got PV, then you can actually identify the equation that you're going to need in order to either find mass of a gas, if you're provided temperature, pressure, volume for that gas, or if to be able to find the molar mass of a gas, which are common questions, and I can tell you, yes, you should know how to do this. So deriving it should be important for you. This equation is not provided in the packet, so you should be able to do that. And so if we're trying to isolate, for example, for the molar mass of a compound here or for a gas, what we want to go ahead and do is essentially just isolate that, bring this over here to the numerator. It's currently in the denominator. So if you do the derivation here, I'm going to skip a couple of steps here, but eventually the mass that you're going to get here is that you're going to wind up with the following. And so that value here, when we do all of that isolation, cross-multiplying, you're going to wind up getting that the molar mass here, big M, I'll use two big M's, molar mass is equal to the ideal gas constant times the temperature divided by the pressure and the volume at the bottom. So that's an important question or equation to know. So make sure you can use that and go forward. Now, if we did not do anything here, and let's say that we took a slightly different route, what if we isolated here the relationship between mass and volume? Essentially, this variable here is equal to density. And so be familiar with the density equation here. So mass over volume is equal to the molar mass times the pressure divided by the ideal gas constant times the temperature. Now, if you need to see those derived, you can definitely kind of look to the notes that I provided already and how we do that algebraically. But these two equations here at the bottom are important equations that you should be familiar with so that you can calculate any problems that come your way with regards to mass or the molar mass of a gas. So that's pretty much it. There's plenty of examples that you can look at, so make sure you pay attention to the links I provided in class off of our class website. Over in the problems or practice problems that you can look at. I believe those links are links number 13, 14, 15, 16, 17, and 18 on the class website. They're very helpful. Look at those in terms of trying to figure out problems for this. Otherwise, you can look at the problem sets, look at the sample problems we did in class in terms of other problems you can look at to look at the concepts here in terms of how you actually solve some problems for this particular section overall. So that's going to bring this to an end here for 3.4. In the next video, we'll look at 3.5 and summarize the main tips there.